Welcome, class. Today we're going to do a couple more examples for this week. First, I want to do an example on the mass conservation principle. So what we have here is a tank, as you can see over here. We have a tank, but interestingly here we have three types of fluids. So at the bottom we have water coming in. Eventually we reach an oil layer, which is going to be here in the middle. And we have a vent where air can come in or go out, which actually we do not know at this point. So what we have here is the tank has an inflow line. I'm giving you the diameter at the bottom. And then you have the diameter at the exit here, 0.8 feet and 0.6 feet respectively. Then what we have is the water flows here at 5 feet per second, and we have an outlet velocity of 12 feet per second. So the question is here, what is the airflow through the vent? How can we calculate this? Well, first things first, we have to identify where are going to be our outlets, right? So we know that Q3 is coming out. The vent, we're going to assume that we have a Q2 also going out. And lastly, we have a Q1 that comes in here at the bottom. So one equation that we can use is going to be the sum of the volumetric flow rates equal to 0. Is that possible? Look at this. What we have is a system that actually has three types of fluids. So we can still assume incompressible flow. And when we assume that, we will know that density is going to be constant, or is not going to change. Another thing we can assume here is going to be steady state. So even though we know that the densities are changing, now you may be asking yourself, how can I do this over this particular surface, or this solution over this particular surface? So we're going to introduce a topic called the control volume. So what the control volume is going to tell you is that you select this surface right here. And what we have, if it is, all of these fluids are incompressible. So what we have in here is that the density overall in the system has to be the same. Nothing is going to be compressed or anything. So what you have coming in will equal to whatever is coming out of the system or control volume itself. There is a differential equation to define a control volume that is written in this form, d dt, the change with respect to time over that control volume times the density and a differential volume element plus the rate of mass going in that direction, rho v dA, over that control surface. So we see here that we assume that our density is constant. So if our density is constant, we can actually take this out of our integral, right? And this equation is also equal to 0. So when we do that, we get rho d dt integral of control volume of a volume, which will be only the volume, plus the rho. We can also take out the density term in there, and we get velocity times area, and that is equal to 0. We know that the control volume, or the volume itself that we have chosen here, is going to be constant, and it will not change. So let's see what does that really mean in terms of how to simplify this equation. Okay, so let's continue here, and we can cancel the densities, right? So what we're going to do now is write the differential equation for volume dv dt plus the integral over the control surface of volume times the differential of area, and that has to be equal to 0. We know this term is going to be 0 because, as we mentioned before, right, there's no change in volume. So when we also have a uniform velocity here, then what we can do is get this to be an average value, so an average velocity term. And when we do that, what we will get is that the sum of velocity times area over the control surface will be equal to 0. And we know that volumetric flow rate, it is equal to velocity times area. So this is how we demonstrate that the sum of Q must equal to 0 as well. Now let's go back and check how to do the sum of the volumetric flow rates. So we have the volumetric flow rates. We have a Q1 coming in here at the bottom. So Q1 is coming in. And what we have coming out is going to be Q3, which is going to be the oil. And also, in this case, we're going to assume that Q2 is going out. We don't know that yet, but that is what we are going to assume. So what we get here is Q2 equals Q1 minus Q3. Since the problem is not giving us the specific volumetric flow rates, right? We can then estimate this as V1A1 minus V3A3. And this information will help us because now we know the area of a tube or a pipe, which is going to be pi d squared over 4. So we have the velocity of the fluid coming in. The velocity of the fluid coming in was 5 feet per second. Then the area is going to be pi times the diameter, which was 0.8 feet to the second power over 4. This is going to be subtracted times the velocity at the outlet, 12 feet per second, times pi, and the outer diameter of that pipe was 0.6 feet squared, divided over 4. And what we get from this calculation is a Q2 of minus 0.88 cubic feet per second. What does the minus sign mean in here? Well, it means that instead of Q2 coming out of the system or the control volume, we actually have air that is being pushed in here so that the oil can move on this direction. Okay? Okay, so as we demonstrated previously, air comes in at 0.88 cubic feet per second. If you recall, the question, though, was what is the pound mass per time, right? So we know that the density of air is 0.075 pound mass per cubic feet. So to calculate that mass flow rate that is coming in into the control volume with respect to air, we do our volumetric flow rate, 0.88 cubic feet per second, times that density. And we can cancel those terms, and we actually get a 0.066 pound mass per second. And we know that 1 kilogram is 2.2 pound mass. And ultimately, we get 0.03 kilograms per second or 30 grams per second. So actually, in order for this flow to happen, air has to be pushing at this particular mass flow rate in order to move that castor oil in addition to the water pushing at the bottom. Thanks for watching, guys.